My name is Ruben Faze, and today I'm going to be walking through our final project as part of the University of Toronto's 3546 Deep Learning course as part of the AI certification. So let's get right into it. So the name of our project is called Understanding Cloud Organizations from Satellite Images, and this is basically a Kaggle research competition that's being hosted. And we decided to kind of tackle this project because climate change is in the forefront of the news, and researchers and scientists are under more pressure than ever these days to try and get something done about this. And we figured, why not try and contribute a little bit and get into that space and see how we can help via deep learning. Now, before we get into specifics, let's introduce the team. My name is Ruben Faze. We also have Naresh Patel, and we have Nisarg Patel. So we are going to be walking through the problem, the solution, as well as the key findings we found in our journey for this. So as I mentioned, this is a Kaggle competition, and therefore the Kaggle team has provided us with a training and test set, which we'll define a little bit later for you. But we want to show you a little bit of a sample of what this is. So here's an image, satellite image on the left side, as well as the identified classes of the cloud structures on the right. So this is a image classification, object detection, and instance segmentation type of problem, and our model architecture that we use is related to that, and you'll see that as we get into that part of the slides. So what are the classes we're facing? So we have 4 different types of classes for cloud structures. We have a flower, fish, gravel, and sugar type of classes that can show up on any image, as well as we can have either all the classes present or none of the classes present. We can have 1 or up to 4 classes for each image. So Kaggle's training and test set has been provided to us, and we're going to get into specifics for each because it matters. The training set is comprised of 5,546 images, whereas the test set has 3,698 images. We're going to take the test set and just shelf that to the side for a second, and we're just going to zone in on the training set, and we'll explain why as well. So the training set, we took a 80-20 validation split. So that resulted in 4,436 observations left for training and 1,110 images as part of our validation set. Now, the reason why we shelved our test set is because we didn't have the annotations file, which is also present in the training set. The annotations file defines where the mask segmentations are. Now, without that as part of the test set, it's hard for us to validate if our predictions using our model are correct or not. So we've really focused just on the training set and splitting that off into a validation set, and we've kind of set the test set aside for now. So before we go into any model development, it's good to do a little bit of light EDA. So as we can see here, of the 4 different types of classes, the sugar class is the most prevalent here at 31.70%, and the flower class is the least prevalent at 20%. So right off the bat, you have a little bit of class imbalance, not terrible, but something to tackle regardless for a good solution. We also have 46.6% of empty masks and 53.4% of non-empty masks, and that is just really good to know. So let's run down what our model's high-level configuration looks like. So we went with the mask RCNN pre-trained model as our main model's architecture, because we figured that, one, if we're going to do an image classification exercise, and there's image segmentation and object detection involved, let's go with the state-of-the-art solution and go with the mask RCNN. We also looked into using UNet and others, but we decided we will stick with what we wanted to work with because we have an interest in the mask RCNN as well. We used the COCO weights to do the weight initialization, and we did 1 epoch for the heads training as well as 5 for all of the remaining layers. This took approximately 16 hours on Google Colab using a GPU, and we used the map evaluation metric. Excuse me. Here's an example of a solution mask. We have the sugar, the flower masks on the right side and the original image on the left. And at the bottom here, you kind of have your image with the mask overlay on top. So as you can see, the solution also has to compensate for the fact that there's a big black line in some of the images. And just to highlight, that represents how there was an image taken from one, I guess, orbit, and as the satellite came into another range for the next image, it had to take a separate image and kind of put those together. And that's why there's a black line in between some of those images. And our model has to work through that constraint. So a little bit about our journey. We kind of started off by splitting the data and building the pipeline, and then we moved on to our model development and building out the mask RCNN configuration and how we want to feed the data in. We later moved on to training the data and evaluating it. We spent a little bit of time in hyperparameter tuning, not as much as we should due to the time constraints, but we were finally able to evaluate our model and then finalize the package and get it out. So that's a little bit about the high level of what it took to get to end of job here. So we found that our image classifier had a 24.9% map score, which is your mean average precision. Our validation set, which is the set that the model doesn't see during the course of training, came out to 23.21%. So as you can see, there is room for improvement for our map score, and that kind of ties into the later steps where we mention how additional epochs and image augmentation and a little bit more focus on hyperparameter tuning could improve these map scores. So we'd like to show you a few examples of how our image classifier did. So on the left side, you'll find the actual image with the segmentation maps and bounding boxes. And on the right side, you'll see what our classifier did for the prediction. So as you can see, our classifier was able to identify the fish and the sugar boxes and masks, and that's because they came up to above the 70% confidence threshold, which you saw in our configuration slide just a few moments ago. And that threshold basically determines how confident is this model in predicting a certain class. So if it falls below the 70% mark, it will not identify that class in the predicted image. So in this case, the 2 of the 3 came out, and the gravel on the right side was just too low for it to determine that. Here's another example here of an actual versus a predicted, and in this case, our model did a good job of identifying the mask for the flower class. However, the other instances were not, the other classes were not predicted for, as they fell below the threshold, or our model might not have been able to determine those classes, and that might be due to additional training required or fine-tuning required. So as I mentioned, there are some certain next steps that we would like to follow to improve and augment our solution, and these include training it for 100 epochs around. That's the mark we'd like to see it at. We'd like to also improve, add our image augmentation, especially for the pre-processing, and make sure that different angles, flips, and rotations are taken during the training. We'd also like to experiment with different initialization weights, including the ImageNet one. We like to try PyTorch or different segmentation models such as the UNet I described earlier. And we'd also like to see annotations of the images with segmentation masks. So this brings us to the end of our presentation for the cloud classifier problem. Thank you for listening. I hope you enjoyed a little bit about what we did for our pre-trained network. And if you have any questions, please feel free to ask. My name is Rune Faze, and from the team, thank you for listening.